Section 5.5, areas between curves and average value. So this is an application section, some of the things we can do with integrals. We'll see some applications in business and some cool sort of geometric problems. So let's jump into regions between curves. Suppose we have two functions. Okay, so in this picture here, we've got f of x and g of x. And suppose we want to find the area bounded by those two curves. All right, and sometimes we'll be looking over an interval, like in this case, we can see on the x-axis we're looking between x equals a and x equals b. Or sometimes we'll be using, intersection points of the two curves, but this is something we'll look at, finding the area between two curves. And the way that we can think of this is we can start with our sort of, approximating using rectangles approach. If we take this region that's between these two curves, in this case, f of x and g of x, and split it up into n subintervals and consider those n rectangles. All right, so thinking about it in the sort of, section 5.2 or 5.3, approximating areas between curves. So the width of this rectangle, or any of these rectangles, is going to be delta x, just like before. But how about the height of these rectangles? Well, if we're just looking at the area under the curve f of x, we'd be looking at this rectangle right here, right? Just like we did in that previous section. But the rectangle is going to be a little larger in this case, since we have g of x, for this particular subinterval extending below the x-axis. So we'd want to add to the height of that rectangle that little distance right there. All right. So this distance is just going to be f of x sub k. And this distance right here, for this particular rectangle, this is below the x-axis. Okay, so if we wanted to add that distance to the height of that top rectangle there, really we'd want to be subtracting minus g of x sub k. Right, so we're introducing a negative because this is below the x-axis, so we would get a negative value, but we want to turn that positive because we're trying to add and make this greater height of this entire triangle. Or excuse me, this entire rectangle. So we're actually taking a difference. All right, so that is why, if we look down here, if we're trying to find the region between these two curves, the formula is going to be the integral from a to b of the difference f of x minus g of x. Again, a difference because the height of that rectangle comes from the difference f of x sub k minus g of x sub k. Okay, so really this is the main formula that we need to know for this section. It's not particularly difficult. All we really have to be careful of is that the first function, f of x, the first term in this difference is the larger function. So the function with the larger output values, or I'll just refer to it oftentimes as the top function. And g of x is the bottom function. All right, so that's what's being said in this first sentence of the definition here. F and g are continuous with f of x greater than or equal to g of x on that interval a to b. Okay, so we'll have to be mindful of that when working on these problems. Oftentimes I'll come up with a preliminary graph so that we can see visually and confirm, verify which function goes on top and which one is on bottom. So looking at example 1, we want to find the area between f of x equals 5x minus x squared and y equals x. I'll definitely do a graph for this one, and it shouldn't be too difficult. This is a quadratic function. F of x is a quadratic function. We can factor this. I could factor out a negative x and rewrite this as negative x times x minus 5. And then y equals x, that's just, diagonal line, slope of 1, y-intercept of 0. So a quick sketch of the graph. I'm going to do that right here. I'm going to count up to 5 on my x-axis, because I know that looking at f of x, since it factors in that way, I can see that I have an x-intercept at the origin and then one x-intercept at 5. And if I wanted to, I could pretty quickly find the vertex of this just to get the graph. The vertex, the formula for the x-coordinate is negative b over 2a, ends up being 2.5 in this case. We also could just look, it's going to be halfway between these two x-intercepts. And then I plug that into the function and I get out 6.25. So can count up on the y-axis, 1, 2, 3, 4, 5, 6, 7. And then I'll have a vertex right there. Okay, so the parabola, f of x, looks something like this. Okay, not perfect, just a sketch. And then y equals x, this is a pretty easy one to graph. It's just this diagonal line like that. And now I can see what this region looks like. I can see that the region I'm trying to find, the area I'm trying to calculate is going to look like this. So I might label that, there's my region A. I want to find that area. And like I mentioned before, sometimes we'll be given a left bound and a right bound. Sometimes we'll have to solve for the left bound and right bound. So really, I'm trying to find A and B. What are the limits of my limits of integration going to be for my integral? Okay, because A is going to be the integral from A to B of f of x minus g of x dx. I'm just trying to fill in what are these values, what is the top function, what is the bottom function, and what are these two limits of integration. So I can see now that f of x is going to be the top function, and this red line y equals x is going to be the bottom function. Let's find the limits of integration, and those are going to be the intersection points between these two graphs. So a little side problem here, we have to find the intersections. So find intersection points. And to find these, we just set these two functions equal to each other. So we'll set f of x equal to g of x and solve for x. So in this case, we just have 5x minus x squared equals x. And solving this, I might get 0 on this side of the equation, add x squared to both sides, subtract 5x from both sides, so I get x squared minus 4x. Solving by factoring, I'll pull out an x. And I see that my two zeros, or my two solutions to this equation, are x equals 0 and x equals 4. All right, so what that tells me is that my intersection points are right here at x equals 0. We kind of could tell just by looking at the picture. And this other one up here occurs at x equals 4. And it turns out it's the ordered pair 4, 4. You could plug into either of these two functions, plug in x equals 4, and you'll get the same output of 4. But really, I just care about the x-coordinate because if I look at my integral, we are integrating with respect to x here. So these a and b values that I'm looking for are going to be x values. So here's what we have. We have the integral from, now we know we're going from 0 to 4, of the top function, which we've confirmed by looking at the picture, is f of x, so 5x minus x squared, minus g of x, which is just x, that's the bottom function, dx. All right, so that's really the only new thing that we're doing here, like as far as finding areas between curves, because at this point it's just a definite integral. We know how to deal with these now, so really setting up the integral, finding those limits of integration, setting it up correctly. You know, if this was on a test and it was a 10-point problem, that might be 6 out of 10 points right there, just getting that integral. And now we just have to evaluate it. So let's do that. I'll simplify a little bit. Subtracting x from f of x, I'm going to get 4x minus x squared dx. And I'll take an antiderivative, and I will get, let's see, 4x squared over 2 minus x cubed over 3, and we're evaluating that from 0 to 4. Okay, so I can simplify a little bit, and I'll write this as just 2x squared, but I'm going to go ahead and plug in 4. So minus 4 cubed over 3, and then we'll subtract from that, plugging in 0, which is going to be 2. Oh, sorry, I forgot to put the second power up there. 2 times 0 squared minus 0 cubed over 3. And that whole thing on the right goes to 0, so I'm just going to have, let's see, 32 minus 64 over 3, and then, minus 0. And you can simplify this. I got common denominators and subtracted these values, and I was left with 32 over 3. Or you could write that as 10 and 2/3. Either is fine. And since we were asked to find an area, I'm going to give my answer with units squared. And sometimes I like to express areas as a mixed number like this so that I can look at the picture and make sure that it makes sense. Sometimes that's helpful, just to sort of check your answer, not a super bulletproof way of checking your answer. But sometimes I'll look at the picture and think like visualize a rectangle around it. Like, okay, that rectangle, that's a 4x7 rectangle that I just drew in red. So, 4 times 7, that's 28 units squared. And the area A looks like it's, a bit less than half of that. So, this number, 10 and 2/3 units squared, like that kind of makes sense to me. I just do little things like this to check as best I can. Because sometimes you'll get a wild number right here. What if I got 100 and 2/3 or something like that? You know you're way off. So little sanity checks are a good idea. Okay, but that's mostly the process, right? Draw the picture, figure out what's the top function, the bottom function, find intersection points if you have to, and set up your integral and evaluate. Let's try another one. Example 2. We want to find the area bounded by this cubic function, y equals x cubed plus 3x squared, and y equals 4x. All right, it would be a good idea to graph this, and I think we could do this without too much trouble, because this equation I could factor out x squared, and I'll just be left with x plus 3. And that's helpful because that gives me a couple of zeros. Do a little graph here. So I have zeros, I have x-intercepts at x equals 0 and x equals -3. So I might set my scale like this. How about? Okay, so I know that for this function, how about I graph it in purple? I'll have an x-intercept here, x-intercept here. And you might remember from college algebra, since this 0 is being squared, I know that it's going to be a bounce off of the x-axis at that point. And I know that my end behavior is going to go down to the left, up to the right, just looking at the degree and leading coefficient of the polynomial. So I'm using some skills that learned back in college algebra. But the graph looks like this. Okay, and this is just a sketch, but the graph looks something like that. And f of x equals 4x, y equals 4x, the second curve. That's just going to be a linear function, so I'll graph it in blue, and it goes something like this. Okay, and I might extend my purple line here down a little bit, just because I anticipate an intersection point down there. So this is a pretty interesting region that we're going to be looking at here, because I'm noticing more than one region that's being formed here. We have this sort of large region here. We have this large region here. And then looking over here, we can't really see it, but in between these two curves, I think we have a very small region. Could try to highlight it a little bit. So what I am now paying attention to is I'm going to go through the process of solving for those intersection points. And the number of intersection points is going to be really crucial, because if I get 3 of them, if I get an intersection point down here, I know I have this one at the origin, and then I have one more up there. And that's what I'm expecting. We'll have 2 regions, so we'll actually have to evaluate 2 integrals. So let's see. Let's find the intersection point. So I'll do that here. And just like always, we'll set these 2 functions equal to each other. So x cubed plus 3x squared, and set that equal to 4x. And this is a polynomial equation. I'll get 0 on one side and try to solve by factoring. That's kind of the standard approach. X cubed plus 3x squared minus 4x equals 0. I'll pull out a common factor of x and hope that I'm left with a factorable quadratic. And I think that I am, because, okay, normally I would put constant value up here, x coefficient down there, and I want 2 numbers that multiply to -4 and add to +3. 4 and -1 do that. So that's good. This factors to x times x plus 4 times x minus 1. So that shows that I have x equals 0 as a solution, x equals -4, and x equals +1. So this confirms my suspicion, based on the graph, that we have a compound region here. So we have this region that goes from -4 up to x equals 0, and then from 0 to +1. So I might label each of these. I'll call this area 1, and then that little area in there I'll call area 2. Okay, and now I'm ready to start setting up some integrals. In this case, we have a compound region. So that's what we're talking about here. Compound regions, sometimes more than one region will be formed by overlapping two functions, two graphs. So in this case, the area, the total area, is going to be equal to A1 plus A2. And now we're going to set up a couple of integrals for these two areas. Area 1 goes from -4 to 0, so those will be my limits of integration for that one. And now what's the integrand? What goes on the inside of the integral? As always, we do top minus bottom. So what is the top function for area 1? The top function is going to be the purple line, which is our cubic function. So I'll fill in x cubed plus 3x squared. And I want to subtract from that the bottom function, which is 4x dx. There is the integral that will give us the area for area 1. Now we want to add to that area 2, which is going to be another integral, in this case from 0 to 1. We're looking at that little sliver of a region to the right in the first quadrant. And we're going to do top function minus bottom function. What is the top function? Well, if you zoom in, like what happens is the purple line and the blue line actually cross over each other, and the purple line goes below. So they switch. Now the top function is actually 4x, and the bottom function is x cubed plus 3x dx. So notice that we never would have figured this out. We never would have known what the top and bottom function are without the graph. You could do like test values, like you could pick a value, like if you really didn't feel like graphing this, you could, pick a value from this first region, like take -2 and plug it into both functions and see which function gives you the larger value. You could do something like that. But in this class, I let people use graphing calculators. You can use graphing calculators on the exam. So oftentimes, we're just plugging this into our calculator and looking at the graph. So you should be able to see. So that's the approach I recommend. Okay, but just to illuminate this, or to highlight, this is the top function in the first region, but the bottom function in the second region. So you really have to be careful and paying close attention to that. But now that we have that done, we just have to evaluate some integrals. So let's do that. I'm going to do both of these simultaneously. So simplifying the first one, I'll just write this as x cubed plus 3x squared minus 4x dx plus, second integral goes from 0 to 1 of, I'm going to write it, oh sorry, I forgot the x squared over here. I'm going to write it like this. How about just 4x minus x cubed minus 3x squared. Very common to forget that we have to distribute this negative sign. Like every one of these areas between curves problems involves subtraction of two functions. And whenever we're subtracting something that has, where the thing being subtracted has more than one term, we have to be sure to distribute that negative sign. So that's a very common mistake that we're not going to make this time. All right, now we'll find some antiderivatives. From this one, I'll get x to the 4th over 4 plus 3x cubed over 3, so it's just going to be x cubed minus 4x squared over 2, or just, minus 2x squared. We're evaluating that one from -4 to 0. Plus, over here, we'll get 2x squared minus x to the 4th over 4 minus x cubed. And we're evaluating this from 0 to 1. Just checking my work. I always like to give it a once over before I move on. Okay, so note that we have 0 as our upper limit of integration for this first integral and 0 as our lower limit for this one, which is really nice oftentimes. And in this case, notice that each of these expressions, if you evaluate them at 0, the whole thing goes to 0. So we get some nice stuff here. This first term is just going to be 0, and then we'll subtract from that. Plugging in -4, we end up with 64 minus 64 minus 32. Okay, so that was just plugging -4 into this expression. And now we're going to add to that. So that was our, first integral. And now for our second integral, I'll plug in 1, which just gives me 2 minus 1/4 minus 1. And then subtract from that, plugging in 0, which just gives me 0. Okay, and then we'll distribute this negative in there. And, also 64 minus 64 is just going to go to 0. So I'll end up with positive 32 from that, and then add to that over here 2 minus 1/4 minus 1. That ends up being 3/4. You could get common denominators to get that value. And then, again, getting common denominators between 32, getting a common denominator of 4 and adding those two together, I'm left with 131 over 4. And this fraction does not reduce at all, so I could just put units squared on this and put a box around it. Okay, you could express this as a mixed number or a decimal if you felt like it. Up to you. But that's it. Since we did both of these integrals at the same time and added them together, that is the sum of area 1 and area 2. That's going to be the entire region bounded by these two curves. One question that you might have is, what about this region over here? Right? There's like a region there between the two curves. What about down here? Why are we not worrying about that region down there? Well, because it's not bounded. Notice that these two curves are just going to, focusing on the right here, this one's going to keep going that way, this one's going to keep going that way. They're never going to converge again. They're not going to create a finite region. So one of the very key words in this is the area bounded by these two curves. Okay, so when I'm looking at the picture, I'm looking for specifically bounded regions, meaning regions that don't shoot off to an area of positive infinity. So I'm looking for intersection points. So that's why area 1 and area 2, that's all that I'm really paying attention to when I'm trying to find the bounded region for this problem. Another reason why the picture, having the graph, is so essential. All right, let's try example 3. We want to find the area between y squared equals x and y equals x minus 2. This is a little bit of a curveball here. Y squared equals x. So you could probably guess by looking at the picture, this sideways parabola, that is y squared equals x. This might sort of remind you of some of the equations that we saw in the section on implicit differentiation, because this equation right here, y squared equals x, implicitly defines two functions in x. Because we can solve for y by taking the square root of both sides, and we get y equals plus or minus the square root of x. So really there are these two functions that come out of this. Y equals negative root x and y equals positive root x. All right, and looking at the graph, this sideways parabola, as we know, the graph of y equals the square root of x is just this top half. So we could think of this as like y equals root x. And y equals negative root x, that's just a reflection over the x-axis. So down here, this is like y equals negative root x. This is how we're going to approach this problem. We're going to think of this curve, the sideways parabola, as really being, two implicitly defined functions in x. And now we have to think, how is this going to impact our process for finding this area between these two curves? So we can see a bounded region, this region here in the middle between these two curves. But we have to be careful because when we're thinking about top function versus bottom function, the top function is the same across this whole entire region, right? The top function is just going to be positive square root function. But what is the bottom function going to be? Notice from 0 to 1, the bottom function is the negative square root function. So I'm going to call that area 1 or region 1. But as soon as we get past x equals positive 1, in this region between x equals 1 and x equals 4, now the bottom function is this linear function, y equals x minus 2. Okay, so that's going to make a change. That's going to impact the integral that we'll use to compute that area. So since there's that switch, since there's that change in the bottom function, this is going to force us to look at two separate areas and use two different integrals. So here's what this will look like. The area is going to be area 1 plus area 2. And we're going to have to set up a couple of integrals. So the first one, area 1, the limits of integration, what are they going to be? We're actually given these ordered pairs, so that's very nice. We have this ordered pair here, 1, negative 1. We have this ordered pair here, 4, 2. Those are the intersection points. So for area 1, remember, we're just looking at the x values because we're integrating with respect to x. We're going to look from x equals 0 to 1. And we want to do top function minus bottom function. The top function in this case is the square root, so root x, minus the bottom function, which is negative square root x. dx, okay, so that's area 1. Now area 2, what are our limits of integration going to be? So what are the left and right bounds for area 2? The left is positive 1, so picking up where we left off from area 1, and we go all the way up to x equals 4. Again, just using the x coordinates of those intersection points that are given to us. And now we want to do top function minus bottom function. So top function is, again, square root of x minus the bottom function. Remember, this is where it switches, and now the bottom function is the linear function x minus 2. dx. And now we evaluate this. I'll start by distributing that negative sign over there. I always am careful to not forget to do that. I can simplify this integral as well. I can just write this as 2 root x, right? Because this is really root x plus a positive root x. And then over here I have root x minus x plus 2. Again, being careful, distributing correctly. Okay, and now I'll take some antiderivatives. Remember, the square root of x is just x to the 1/2 power, so I can write this as 2 times x to the 3/2, right? Adding 1 to that exponent, and then I'll multiply by the reciprocal 2/3. And evaluating that from 0 to 1. Plus, okay, again, taking the integral of the square root of x, we'll get x to the 3/2 with a factor of 2/3 out in front, minus x squared over 2 plus 2x. And this one evaluating from 1 to 4. Okay, good. And I'll simplify a little bit. I can write this as 4/3 x to the 3/2 evaluated from 0 to 1 plus, and all this can kind of stay the same. I don't really need to change anything there. So let's evaluate it now. I'll start by plugging in 1 over here. And I might, just to be careful, group that together there, group this together here, just to sort of color code things so I don't get confused about what's going where. Okay, so I'll plug in 1 and I get 4/3 times 1 to the 3/2. And then minus plugging in 0, that just goes to 0, so that's kind of nice. Plus, and now working on the second integral, I'll evaluate this at 4. So 2/3 times 4 to the 3/2 minus 4 squared over 2 plus 2 times 4. And then subtract from that, plugging in 1, which is just going to be 2/3 minus 1/2 plus 2. Just checking my work, being really careful as always. It's a hard problem. It would be a shame to do it twice because you make a mistake. All right, and then moving forward, I'm simplifying. I want to make sure I don't forget to distribute this negative over here, so I'll make those lines. This ends up being just 4/3 plus, so that's the value of that first integral. That's the area, area 1 ends up being just 4/3. And adding that to area 2, this is a little bit of work to simplify, but I'm left with 16/3 minus 16 over 2 plus 8. And then, I'm getting common denominators to add these other values together. I get, so minus, because I'm distributing that negative sign, I'm getting a common denominator of 6 here, so I end up with minus 4 over 6 plus 3 over 6 minus 12 over 6. Okay, so I distributed the negative and got common denominators. And then, I'll spare you all the rest of the writing. I simplified all that stuff in the purple brackets and added it to 4/3. I ended up with 9 over 2 when all the dust settles. So you could express it like that, or 4.5, and I'll put a unit squared on the end. So about 4.5 units. Units squared, that is that entire region bounded by those two curves. All right, and I could do my sanity check thing, like if I drew this rectangle right here, So that's a 3x4 rectangle. So, that whole rectangle has an area of 12 units squared. And it looks like our region that we're looking at is, a bit less than half of that. So 4.5 units squared, that makes sense. That looks about right, just comparing those regions. Okay, so that last step is not necessary, but I like to do it just to give myself a little bit of confidence that I did it correctly. Very good. So that's how we would do that one. This was a difficult problem because we ended up with a pretty bad, arithmetic problem at the end. Simplifying that was a lot of work, lots of places to make mistakes. I didn't even write out all the steps, right? It's a lot of work simplifying that. So this is a hazardous type of problem right here. You have to be super careful, work really slowly, don't rush yourself, take your time. That's the best way to go and to avoid making mistakes. But there it is. Let's move on. Let's talk about average value now. So consider a function f that is continuous over an interval a to b. And suppose we wanted to take an average, find the average value of the function. So looking at all the outputs, what is the average of all those outputs? The challenge here is if f is a continuous function, there are infinitely many outputs between a and b. How can we compute an average with infinitely many numbers? That's the challenge that we're trying to overcome here. Suppose we just approximated the average. Okay, here I'll draw a little picture real quick. Let's say that here's our function f. And if we're looking from x equals a to x equals b, right? And then here's the output. I'll mark this ordered pair a, f of a, and then this ordered pair b, f of b. Okay, so to find the average value between those two x values, a and b, there's infinitely many points. So we're going to take this subinterval approach. And let's say that we just split this into n subintervals and calculate all those outputs. So f of x sub 1, f of x sub 2, all the way up to f of x sub n. Add them together and divide by n, right? That's going to give our approximate average value. Okay, so that's what this is right here. This is the approximate average value. All right, next we're going to rewrite this in terms of a Riemann sum. Because remember, this n, the number of subintervals, is equal to b minus a divided by delta x. Okay, or I think the form that we actually have seen this before is we had that delta x was equal to b minus a over n. So notice that we just multiply both sides by n, divide both sides by delta x, and we could also get that n is equal to b minus a over delta x. So we're just making that substitution in this formula. Notice we substituted in for n, b minus a over delta x. Okay, so we're going to take this, and we're dividing by a fraction here. So another way we could write this, sorry, I have to get this out of the way, is to divide by a fraction is the same as to multiply by the reciprocal. So we can rewrite this as f of x sub 1 plus f of x sub 2 all the way up to f of x sub n times the reciprocal delta x over b minus a. And I want to take this delta x and I want to distribute it into every term that's in the numerator. And I'll be left with this fraction. And then the 1 over b minus a, I'm going to bring that out in front. So 1 over b minus a, that'll be out here by itself. And then distributing the delta x on the inside, we'll get f of x sub 1 times delta x plus f of x sub 2 times delta x all the way up to f of x sub n times delta x. So just manipulating this a little bit algebraically. And what we have here is, okay, 1 over b minus a is still out here off to the side. But inside of the parentheses here, we're left with a Riemann sum, right? This is the sum from k equals 1 to n of f of x sub k times delta x. So if we wanted to do the thing that we did to define the definite integral, where we take the limit as the number of subintervals n goes to infinity, we're going to be left with a really nice formula for the average value. So I'll say now we want to take the limit as n goes off to infinity, and we're left with this. The limit as n goes to infinity of 1 over b minus a times the sum from k equals 1 to n. So just our Riemann sum. And 1 over b minus a can come on the outside of the limit. What we're left with is 1 over b minus a times the integral from a to b of f of x dx. This is our exact value. Rather than an approximate value or approximate average value, this is the exact average value of the function. So that's how we derive this formula here. So I'll highlight this. This is our formula for average value using the definite integral. And just spelling that out down here in this text box, the average value of a function, let f of x be a function that's integrable on the interval from a to b. Then the average value function, f, and we put this little bar on the top, sometimes I'll call this f bar, of f of x over the interval from a to b is given by that formula we just derived, 1 over b minus a times the integral from a to b of f of x dx. And the sort of visual graphical interpretation of this is if we took the area under the curve from a to b of f of x and just sort of compressed it into the shape of a rectangle, the height of that rectangle is going to be the average value of the function. Okay, or sometimes I've heard this talked about, like, you know, say we had like water in a container. You know, like if I had water, like if that's our f of x looks something like this. And we have this tank filled up with water. You know, we have like a certain determined amount of volume here, but it's just sort of compressed into this odd shape. What if we just took the top off of this and let the water settle? Right? And let the water settle into just sort of a standard rectangular shape. Right? The shape would still have the same width as before. But it would reach equilibrium and it would just reach a height that would end up being the average value of the function. Okay? Okay, so that's just the geometric interpretation of f bar, of our average value. Let's find some average values. Here's a typical example. The elevation of a path, you know, so maybe some trail or something like that, is given by f of x equals x cubed minus 5x squared plus 30, where x measures horizontal distance. Okay, and then the output value is the elevation. Find its average value from 0 to 4. All right, so we're essentially, you know, like we're on a hike or something like that, and we're hiking for 4 miles, let's say, and we want to know what's the average elevation of this path. That's what we're going to find. So it's graphed over here to the right. Let's apply this formula. The average elevation will just be the average value of the function f. So it's going to be f bar. So let's find f bar. This is going to be equal to, the formula is 1 over b minus a. What is b? What is a? So we're saying average value from 0 to 4. So 0 is the left endpoint, 4 is the right endpoint. So 0 is going to be a, 4 is going to be b. So down here we'll do 4 minus 0. And then the integral from 0 to 4 of f of x, which is given to us, it's the cubic function x cubed minus 5x squared plus 30 dx. Okay, so simplifying a little bit, this is just going to be 1/4. And then I think we could do the antiderivative now. Anti-differentiating, we'll get x to the 4th over 4 minus 5x cubed over 3 plus 30x, and we'll evaluate that between 0 and 4. So we'll have 1/4 times, okay, plugging in 4, we'll get 4 to the 4th over 4 minus 5 times 4 cubed over 3 plus 30 times 4. And then minus, this whole thing evaluated at 0. This is one of those nice ones where we just get 0 minus 0 plus 0. So that all goes away. That's nice. Okay, and then simplifying 1/4 times, this is going to be 64 minus 320 over 3 plus 120. Okay, and then simplifying this, I got common denominators on the inside, and then multiplied that by 1/4, and I was left with 58 over 3. Or this is approximately 19.3, putting that into my calculator and rounding to the nearest tenth. And then we would include our units. Let's assume it to be feet. I'm noticing that there actually aren't units listed here, but we would normally include units down there. And that would be our answer. Okay, so really not an incredibly difficult formula to remember. It's just the integral. It's basically the area under the curve divided by 1 over b minus a. So the only new thing is that factor of 1 over b minus a at the beginning. Okay, so we do have some new formulas in this section, but nothing that's super out of control, right? The last applications we were doing with the areas, it's just, the integral of top function minus bottom function, right? And finding those intersection points. And then the average value function. So the hardest part of these problems is really just evaluating the integrals and doing all the arithmetic correctly. I don't think that the formulas are particularly difficult here. Let's try example 5, and I think, this is the last one for this section. A company determines that T months after the introduction of a new product, the company's sales will be S of T, which is equal to 3T root T plus 10. And the outputs of this function are measured in thousands of dollars. What are the average monthly sales of the company after the first 9 months of production? All right. So we're looking for a couple things. We want to know what's the function we're working with, what's the interval we're looking over, and we're going to use that average value function because we're being asked for average monthly sales. Okay. And T is given in terms of months, so average monthly, that's going to be easy to find. So what we want is S bar. We want the average output of S. over this interval from 0 to 9, right? The first 9 months. Okay, so I can point out, A is equal to 0, B is equal to 9. We have our function. That's really all we need to figure this out. So here it is. S bar, the average value of S is going to be 1 over B minus A. So 1 over, I'll write out the formula just to remind us. It's just in terms of T this time. So 1 over 9 minus 0 times the integral from 0 to 9 of 3t root t plus 10 dt. Okay, so this is 1 over 9 times the integral from 0 to 9. This is a weird factor right here. I could think of this as 3 times t to the 1/2. So multiplying those, t times t to the 1/2, I'll just add the exponents. This is 3t to the 3/2, like that. Just rewriting it, setting it up for a nice power rule. And I think I'm ready to evaluate the integral. So I'll do an antiderivative and I'll get 3 times, new exponent, adding 1, t to the 5/2. And then multiplying by the reciprocal, that's the same as dividing by that new exponent 5/2, plus 10t, that's the antiderivative of 10, evaluating from 0 to 9. So I'll have 1/9 times, 6 over 5. And then 9 to the 5/2. 9 to the 5/2 plus 10 times 9. That's that first term, and then subtracting from that 0. Okay, we're fortunate again in this case. Plugging 0 into that antiderivative just gives us 0. All right, and then just another kind of nasty simplification problem. You can approach this however you want to, whatever is most comfortable for you as far as simplifying this. I'm going to spare the details. Here's what I was left with at the end. 42.4. I went to my calculator at a certain point because I had to divide by 9. 42.4, that's the value that I got after simplifying all of this. 42.4 what? What are we talking about here? This is the output, the average output of S. What does S measure? S measures sales in thousands of dollars. Okay, so $42.4 thousand. That's a little weird. I wouldn't normally say $42.4 thousand. I would rather just multiply. This is really 42.4 times 1,000 times dollars. So I would write my answer like this. $42,400. And I'll box that up. Okay, so we can do that. We have a function that models sales or profits or costs or revenue or what have you. We could use this formula and integration, definite integrals, to find an average value without too much work. So there are a couple applications for you, and that brings us to the end of the section. Next up, we're looking at substitution rule. Currently, we're pretty limited in what types of integrals we can evaluate using antiderivatives. We need a couple more tools, so section 5.6, we're going to explore those. So I'll see you in that next video.